Warm greetings. Welcome to Wednesdays for Water. We are a citizens collective aiming to walk and talk water. We try to meet every week and connect people with various water worries and wisdoms. And in the process, we wish to curate future water warriors. The way we talk about trivial things for hours, water too needs walking and talking to address the rising water distresses. The way Wednesdays for Water is conceptualized as a prime time show, it wishes to make water everybody's business. The idea of the series was conceptualized in August 2020, and by the end of the year, the team and the structure was pretty much in shape. We started in April 2021 with Dr. Rajendra Singh's inaugural speech. We wish to bring science and society together, and therefore we try to bring in every session either a policymaker or practitioner and a researcher or academician. We also think that future generation is crucial and therefore they have presence in each session. We are going stronger with every week now with session on either quiz, couple of weeks of hard talks, and a week of soft session of art and music. There is a simple structure for each session of quiz, hard session, and soft session, which are moderated by the core team member. Here is a glimpse of what we call as hard sessions and soft sessions.
Yes, good evening, everyone, and thank you for joining us for an interesting Wednesdays for Water session on the theme of wastewater treatment and environmental sustainability. And the process of wastewater treatment has actually many benefits, and that makes it very important for achieving environmental sustainability in the short term, medium term, and long term. So to discuss various aspects of wastewater treatment and environmental sustainability, we have two very important speakers with us, Dr. Kirti Yenkie and Mr. Andrews Jacob. I would like to thank both the speakers for joining us today. I'm the moderator today. I'm Suparana from TIS, Hyderabad. And I would like to take a few minutes to introduce our speakers to the participants. Dr. Kirti Yenkie is an assistant professor at the Henry M. Rowan College of Engineering, which is a part of the Rowan University in New Jersey. She has more than 10 years of experience in process systems engineering with a focus on sustainability. She has more than 10 years of experience on the themes of sustainability and environmental resources management. Her ongoing research projects are on green engineering, wastewater asset management. She's leading the sustainable design and systems medicine lab at RU. She holds an MTech from IIT Bombay, a PhD from University of Illinois, Chicago, and has gained postdoctoral research experience from University of Wisconsin, Madison, and University of Delaware. Our second speaker is Mr. Andrews Jacob, who is a senior project manager at Consortium for Devotes Dissemination Society, which is in short known as CDD Society, based in Bangalore, India. He is a water and sanitation professional focusing on planning and implementing nature-based solutions in wastewater management, fecal sludge management, water body rejuvenation, integrated urban water management, and solid waste management. He has more than 13 years of experience in implementing projects and building capacities in India and abroad. He's currently focusing on linking nature-based solutions and climate initiatives towards resilient and sustainable cities. So before we begin, I just have one or two housekeeping announcements that we are recording this session and we would like to take your permission to do that. Thank you so much for granting us the permission to record. We also request all the participants to keep themselves on mute so that we can hear the speakers better. And we also welcome the participants to raise questions in the Q&A session as well as post the questions in the chat box, which we'll take up in that Q&A session. So without taking any further time, I would like to now invite Dr. Kirti to share her research and perspective on the theme of synthesis of efficient wastewater treatment networks via the P-graph approach. Dr. Kirti, the screen is yours.
Thank you so much, Dr. Suparana, and I thank the Wednesdays for Water community for the invitation and allowing me to share my work. So as mentioned, I will be talking about the synthesis of efficient wastewater treatment networks via the P-graph approach. So before I go into that, I also would like to talk a little bit about my university. So Rowan University, it is a public research university in southern New Jersey, and it is located close to the city of Philadelphia, as you can see in the map here. The College of Engineering was not initially part of the university. It was established in 1992 after it received a gift from Henry M. Rowan to build an engineering program which was not present in the southern Jersey parts of the country. The first graduating class was in 2000, and then currently we have 6 bachelor degrees program, including chemical engineering, civil and environmental, electrical and computers, mechanical, biomedical, and experiential engineering. We also have a master's and a PhD in engineering program. And then this is one of the fastest growing research university. So I'm glad to be part of this institute. With that, I would now like to talk a little bit about the overview of my talk. So first of all, as my area is systems engineering, which is mostly related to mathematical modeling, optimization, and control, I would like to pose the wastewater treatment problem and explain why systems engineering or modeling can help us with efficient synthesis of these networks. Then the designing aspect and what goes into the process. Then I will explain a methodology which is based on graphs and networks, known as the P-graph method. And then I will demonstrate this approach via a case study, which has the municipal wastewater, some results, and then conclusions and future work. So I think this community is well aware that we do need to look into other aspects of recovering water, because if you look at the total world availability in regards to water, many of it is in the form of oceans, which are highly salty. We cannot use them. We only have about 2.5% of freshwater resources. And in that also, most of that is in the form of ice and snow. So that leaves us with very little freshwater and groundwater resources. And if we look at the overall statistics of how global water consumption has been increasing in the past, I would say around 125 years, we can see that there is an increase in all the continents of the world. So this increasing demand, but we do have the resources which remain constant. And that is where we have to come up with a solution where we can meet the increasing demand for water. And that is where treating and recycling water could be an alternative. In order to do that, we need to come up with efficient wastewater treatment methods today, so that in the future we can satisfy these growing needs. And everything, when we start with something, it takes a process. We have to work on that and improve it further so that we can finally get something which is more sustainable. And that is where systems engineering can help and provide you with some sustainable as well as cost-effective insights, because we do want to be cost-effective as we are looking at treating waste, and we cannot, we also have to balance the overall cost as well as environmental impact whenever we are designing a new process. So as I mentioned, process systems engineering, it encompasses multiple dimensions. It includes data analysis, mathematical modeling, process design and operation, process control, optimization, risk analysis, and quantification methods. Now, these are all related to more computational side of things, but if we look at the wastewater treatment problem and try to analyze it in a systematic way, what do we see? That wastewater can come from multiple sources or multiple industries and areas. So we could have wastewater coming from a food industry, which could be large in volume, and most of the waste could be starches, then food colors and all those kind of agents. Pharmaceutical is another type of industry. The wastewater here would be containing active pharmaceutical ingredients and maybe some hazardous solvents. So in those cases, treating the wastewater will be very different as compared to what you would do in a food industry. And you can see many other aspects or many other areas from where we can generate or we can find wastewater. Power plants, hydrothermal power plants usually use them, chemical industries, also domestic sources, agriculture, and so on. And if we look at the available treatment methods, there are multiple options. We can use activated carbon, we can use disinfection, membrane processes like reverse osmosis, and so on. We can also use UV sterilization, advanced oxidation or ozonation processes, settling tanks, and so on. So in order to find out which particular method or a combination of these methods would treat a specific type of wastewater more effectively, we have to match them well and then decide on a cost-effective as well as a sustainable process. So in that sense, this appropriate selection becomes a systems engineering problem. And then when we look at the overall complexity or what goes behind when we try to design a systematic treatment process, let's look at just one of the tasks, which is solids removal. Solids can be removed via multiple technologies. We can use sedimentation, which is based on gravity settling. We can either go for a membrane process, when the pore size of the membrane as well as the overall permeability of the component will decide what will be separated. We can go for filtration if the particle size is larger, and we can use regular filter presses. We might also do screening if we have large grit particles and gravel, or sometimes if the particles are lighter, then we could use a flotation technique. Now, for a simple task like solid removal, I have provided that there are 5 different methods and there can be many more. So if we look at the total design of the problem, let's say if we had about 5 components in a stream, so this could include solids, solvents, active pharmaceutical ingredients, let's say around 5 such components. And then we have 10 different technologies to treat them. Overall, if we were to look at the possible combinations or possible networks which we could have, they are around 140,000 possible networks. Out of them, not every network will be feasible because it will not take you to the desired purity or whatever guidelines or things you need to meet, right? So only some of them will be feasible, and among those feasible networks also, some of them will be more cost effective as compared to others. Some of them would be more sustainable as compared to others. So that is where the problem becomes a more systems analysis or detailed mathematical analysis problem. So as well known in most of the wastewater treatment and engineering textbooks, we will see that if we divide the wastewater treatment in a stage-wise manner as seen here. So I have taken this from some of the standard books like Metcalfe and Eddy, and you can find more details in one of our papers on how these technologies have been segregated into stages, as well as what are their model equations which are used in our models for finding the appropriate network. So if you see, pre-treatment is mostly to facilitate solid removal, and it includes flocculation. Flocculation is basically adding a flocculant that leads to formation of clusters of particles which become higher in density, and then you can remove them via settling. Screening I already talked about. Then sedimentation is based on settling due to gravity, filtration, and so on. These are mostly for solid contaminant removal. Secondary are to remove chemical and biological contaminants, and there are multiple options here as well. And in the tertiary stages, you're basically trying to remove some of the recalcitrant solids or some of the contaminants which could cause coloring or like undesired appearance of water. You're basically trying to improve on them by using some of the advanced techniques. Okay, now that is why by using these criteria, they have been placed into 4 different stages. Using this idea, the next approach which we are applying to design of wastewater treatment networks is based on graphs. So I think we all are aware that graphs are basically some connections which connect one particular node to the other via arcs, connecting arcs. So if we look into the P graph, what we have done here is that the materials, so particularly the components present in the wastewater stream as well as water, these will be categorized as materials. Raw materials are something which are entering the system. So these could include high level of contaminants, water as well. And then the product would be our, so sometimes we might just physically remove these contaminants. So the product subset would still be the same. Sometimes we might have some chemical changes. So then this product subset could be altered. And then not every time we will just have one stage, right? We might have multiple stages. So these would also generate intermediates. So these are the representations in P graph, and each of them have a certain property. So for example, a raw material would be that it does not have any input going into it, but it will only have a certain output arc leaving the raw material. Product would be that it will only have some input arcs coming to it, and it's a terminal node. So these properties are already well established, which helps us in generating a network. And then operating units are represented by these horizontal bars, which are our technologies. And in this technology, you can provide the details of cost. You can also provide details of sustainability. And that is how you end up formulating the complete network. And these, for determining among the available networks, to determine the structurally feasible ones, there are certain axioms and properties which will help you in finding out which of these networks are feasible as compared to the others. And the algorithms which are available include generation of the maximum possible structure, the solution structure generation, and then to give you the exact value of cost and rank your structures, that is accelerated transit bound. And since these are more mathematical, I'm not going into the details, but if you are interested, I have also provided some resources to the Wednesdays for Water community, and you can find more information there. So with that, this is our framework which we are applying to wastewater treatment network. And the case study currently which we are looking into is the municipal wastewater treatment, where we have categorized things into solids, chemicals, and then of course water, which we are trying to recover. These are the inlet amounts in kgs per hour. And then the purity requirements have been given here, that we at least want to remove the solids, and if they are around less than or equal to 500 kgs per hour, we are good. It's okay for disposal. Chemicals should be less than equal to 5 kg per hour, and so on. And then we also want to recover at least 80,000 kgs per hour. So these numbers are taken from this source. And here I'm looking into the different technologies which are used in our treatment network, which includes sedimentation filtration. And as we can see that the the technologies which remove solids have a certain solid removal efficiency number. So 85% for sedimentation, 90% for filtration, and so on. And for chemicals, we are including rotating biological contactors, adsorption and disinfection, and advanced oxidation process. So with these numbers, when we input them into the system, the other thing is we also need to analyze what are the potential structures, or you can say the overall networks which are feasible. So in that case, when we try to generate this maximal structure in stage 2, which is mostly for solid removal, we have sedimentation, filtration, and membrane processes. Sedimentation being a low efficiency technology, sometimes depending on your requirement, it might be followed by filtration, it might be followed by membrane. Similarly, filtration would be lower in efficiency as compared to membrane. So filtration could be followed by membrane. But you should also have the opportunity, if let's say your wastewater has, if your treatment has removed the desired amount of solids, then you can remove and take your treated waste, the treated water stream to the next stage from these particular nodes. Okay, so this generation of the maximal structure is of essence. That is what can capture the maximum possibilities. And when we do that, we have, as we can see, there are 7 potential nodes here. And then there are 8 such operations, because we can also bypass stage for solid removal. We don't need that. So that makes it 8 operations. Similarly, if we look at the next stage, which is stage 2 and 3, that leads to 18 such operations. And this is the entire structure which we should analyze if we want to look into all possible methods, as well as find out the most cost-effective and sustainable option. So this exhaustive enumeration is important. And then this is the overall methodology, that after we write down a case study with the different contaminants and also the water, we formulate the synthesis problem, which includes our input stream composition as well as the requirements of the final treated stream. And then we list our technologies, generate the exhaustive structure. We define our cost estimation model, our efficiency or the recovery ratios, and then we construct the entire problem structure using the stage-wise approach and solve for feasible paths. And then the accelerated branch and bound is what leads to the identification of all the optimal structures, and it also ranks them on the basis of the metric. So let's say if you want cost to be the metric, it will give you the lowest cost followed by the next best, followed by the next best. If it is a sustainability index, then it can also do that. It can rank that on the basis of, let's say, land area occupation or sustainable process index, which I will be talking about a little bit later. Okay, so with that method, the overall network structure, as you can see, we can now visualize this in the p-graph step, where we have these particular technologies and options for solid removal. Then we have the second and third stage as shown here. Okay, and then the second and third stage is elaborated in this particular diagram, and we can clearly see the type of nodes we have for raw materials, products, and intermediates. Okay, and finally, this generates a big structure like this. And due to the ability of computational methods and the p-graph axioms, we can solve this particular problem within minutes, and we get the best possible treatment path as shown here. And finally, since I mentioned that it gives you all possible feasible networks, overall, we actually generate around 1,200 such feasible networks. Out of them, I'm only showing you the first 4 optimal structures. And as you can see, in the first one, it just gives you membrane followed by adsorption. And this is the cost number. Then in the second option, the cost increases a little bit. Okay, it just goes from 12.49 to 12.65 cents per liter. But if you look at the structure, we now have membrane followed by rotating biological contactors, adsorption, but it asks you to bypass around 21%. So some of these things might not be clearly visible when we are designing treatment networks in a traditional way. We can get more non-intuitive and optimal solutions if we go with some of these advanced modeling techniques. And with better computing facilities, these are possible. So that is why we are looking into analyzing treatment networks in a much better way. More details about this exact case study can be found in our paper, which is in the AICHE journal. And the materials which I distributed includes a Excel tool as well as supplementary material for you to understand this case study. So along with that, we also did some parametric studies. Parametric studies help us in understanding how sensitive our optimal network is. So for example, sometimes our wastewater treatment composition can change. Our amount of chemicals can change, amount of solids can change. So for example, let's say if the chemicals are changing, then we will basically change the value of the arcs or the amount of inlet chemicals into the water. And when that happens, our best structure, so let's say if the chemicals change to 10 kilograms per hour, then our best structure changes. It's no longer, it was earlier filtration followed by RBC, but then there is a little bit of a bypass happening because the number of chemicals are lesser. Then if it goes to 50 kgs per hour, then it changes from filtration to membrane, and then so on. Similarly, if we change the recovery requirements for chemicals, so instead of 10, we make it 0.5 or so, then we can see that different technologies get selected. And these things are, these results are, you can obtain them within minutes. It doesn't take you a lot of time because of the capabilities of the solution algorithm. And there are other ways in which parametric analysis have been conducted. Due to limitation in time, I'm not going into these details. But as I mentioned, the AICHE journal paper talks about all these parametric studies in more detail. So along with that, the same index, like the cost index, can be replaced by a sustainability index like the sustainable process index. So sustainable process index, it is a reasonable metric. Why? Because you can map everything into one particular metric, which is the amount of area needed to embed either your inputs, services, as well as whatever outputs are being generated. So in the input, which can include your raw materials, it could comprise of renewable, non-renewable sources, energy consumption, staff requirement, and whatever installations you need to conduct for your running of the plant, wastewater treatment plant. And then you also have your process which generates certain products. So in this case, it would be the treated water. And then in the process, due to the technologies, you might have some air, water, and soil emissions. Everything as it gets mapped into the single unit of per unit area, that helps in getting you a single metric, like cost is one metric, SPI becomes one metric, and then you can analyze the same network in terms of SPI. So as I mentioned, I'm not going into details of how this is done, but you can find more resources and the detailed description of SPI can be found in this paper, which talks about SPI application to solvent recovery. And we are currently working on incorporating this in the design of the wastewater treatment networks as well. So in summary, I talked about how integrated design and optimization can help us in generating efficient wastewater treatment networks. The P graph is based on a simple graph theory, which includes set of nodes and vertices. And based on certain axioms which P graph follows, we can get detailed insights into costs, as well as it can lead to some non-intuitive solutions. We are extending this to apply to more complex wastewater treatment structures, as well as we are including the sustainable process index to incorporate sustainability in our evaluation. And the PGraph tool in Excel, which is provided in this particular link along with the supplementary resources, it allows for simplified use and analysis. And with that, I would like to also mention that this work has been possible through the work of my students, as well as my collaborators, Dr. Cabezas and Dr. Friedler from Hungary, their students, and then the graduate student Emmanuel Aboaje is one of the primary students working on this, and he has mentored 3 undergraduate students, and they have also helped in writing our publications and helped in disseminating our work. I also would like to acknowledge the funding which we have received from US EPA, as well as Atlantic County Utilities Authority. We are doing some of the wastewater asset management work for ACUA, and that has also helped us in understanding the wastewater composition a little bit better. And my Department of Chemical Engineering at Rowan University, and my students from Sustainable Design and Systems Medicine Lab. With that, I thank you all for listening to the talk, and I look forward to your feedback and comments. You can find more information about our work at my website, and if you have any questions later on as well, please feel free to email me. Thank you so much.
Thank you so much, Dr. Kirti, for a comprehensive presentation on wastewater treatment network. I come from a non-engineering background, and I found this really, really insightful. And now I understand how decisions on sustainability can be made through such a intensive exercise and the knowledge that has been created by you and your team. So it was a pleasure to see how you have acknowledged your team as well, where there are young people as well as senior faculty. So that is what we are trying to promote through this platform, connecting the senior researchers, senior practitioners with the youth. And thank you so much for, doing that. So now we would like to continue thinking along wastewater treatment and environmental sustainability with Mr. Andrews. And I'd like to invite him to share his experiences and perspective on how nature-based solutions and systems are the need of the hour when we talk about wastewater treatment. The screen is yours, Mr. Andrews. Thank you.
Okay, thank you so much. I thank Wednesdays for Water Group for making this opportunity to talk to you all. And I thank Dr. Kirti for the wonderful presentation. It was very interesting. Sorry, my voice is slightly bad, but I will try to manage it. I hope you'll be able to listen. So now we are going to talk totally a different scenario what Dr. Kirti talked. It is going to be a decentralized wastewater treatment approach. Also, how a nature-based system can be approached, or a nature-based system can be utilized in decentralized wastewater treatment systems. My name is Andrews Jacob. I'm from CDD Society. CDD Society is a not-for-profit organization in Bangalore. This is our office, a very beautiful office. These are our network partners, pan-India, and we have partners from other countries of South Asia. CDD works mainly for wastewater treatment and fecal sludge management, water body rejuvenation, solid waste management, and integrated water management, integrated urban water management. Across this, we do a planning, design, and implementation of projects. We conduct capacity building programs and trainings. We also conduct applied research, and we also develop knowledge management documents and communication materials. These are our donors and key partners. Now, coming to the point, we have a Center for Advanced Sanitation and Solution, which has the training unit where people can come and take training on water and sanitation. We also have our NABL accredited laboratory where we conduct a lot of innovative research on water and wastewater sanitation. We have a design and production unit where we manufacture the ready-made wastewater treatment systems. And we also have our knowledge management unit where the many publications can be downloaded from our website. And we have one sanitation exhibition where someone comes who does not know anything about sanitation can come as a one-stop shop for understanding sanitation, where someone comes, he or she can understand the issues in sanitation in our country and how that issues can be solved, or what are the possible solutions available. So it's a very interesting sanitation which is designed for school children to professionals. Now I'm going to talk about wastewater treatment in a decentralized way and nature-based way. So this is some scenario, city scenario you see, right? So if you want to provide a wastewater treatment system, you all might know that there are STPs available, sewage treatment plants, which are connected by the underground drainage systems, which we call it as the centralized, centralized treatment systems, or underground drainage systems, where you see all these places can be connected, and this place also can be connected. So in this one, what they are facing is two things. One is the cost, which has to be connected. That the distantly located colonies or houses also have to be connected through pipelines, which costs more. Also, mostly the sewage treatment plants are highly energy intensive systems. So that's where the operational maintenance is much higher cost than implementing the systems. So wherever you go in sewage treatment plant systems, you might see some of them or most of them are not working because they are very cost intentional operational things. Meaning one is the energy intensive, other one is the chemical intensive wastewater treatment systems. So imagine that there are some in a city, the underground drainage systems are connected and they are treated in a common treatment plant or a sewage treatment plant. There are a lot of newly upcoming colonies, households, everything. So you cannot keep on extending these kind of underground drainage systems, where the decentralized systems are much appropriate solutions there. So for example, if you provide a smaller treatment system like that, then you will have a comprehensive coverage of the wastewater treatment systems. So here what we are going to see now is that the quick comparison between the other systems and nature-based systems. The major systems, the sewage treatment plant systems, they might require less land area because they are energy intensive, machineries based systems, and they are using a lot of chemicals. So if you look at the electricity, that is really huge, and wherein nature-based system it is not that much, wherein we might need have some extra area to implement these nature-based treatment systems. Wherein in the annual operational maintenance cost, if you see, any system which will be working with energy and chemical, they will end up paying a huge cost at the end of the year. So then whatever I'm talking about, what is this nature-based treatment systems, you might wonder. So this is just a conventional treatment systems which are already existing, and now these systems which we are just trying to use mimicking of nature, the existing nature treatment system in these kind of systems. So the naturally occurring microorganisms, they treat the wastewater, meaning they eat the organics. Organics are nothing but our feces, also organics. So here I just provided a flow of treatment system. As Dr. Kirti showed in her presentation, the primary treatment system, secondary treatment system, and tertiary treatment system. The primary is basically the sedimentation or settling, which is this kind of treatment system. And the secondary could be either chemical or biological based. In our presentation, you could have seen that. So chemical systems mainly use addition of chemicals for removing of the pollutants, wherein biological systems, they work through microorganisms. So here the system is mainly based on microorganisms. It's an anaerobic system where the anaerobic microorganisms, in absence of oxygen, they treat the organics. Then the tertiary treatment systems comes, which is the polishing of the wastewater. So this is what we are going to just quickly see about how these systems are going to work. In the primary treatment systems, we have a sedimentation tank, or you can call it a settler, or this is nothing but a kind of a septic tank, but with lesser retention time. Retention time is that the number of hours or the water stays within the tank. So when the wastewater raw sewage comes, it goes to the bigger first tank, then where all the sedimentation of the sludge and everything happens, then it goes to the next smaller tank where further sedimentation happens. So here this as a primary treatment system, only sedimentation happens. Sedimentation nothing but separation of water and solid. So here in this treatment system, almost 40% of your solids are settled, mainly the major bigger solids which are actually settled there. The suspended solids in the wastewater will go for the next biological secondary treatment, where this is the series of chambers where the water is allowed to go through in an upflow direction. So you might know upflow anaerobic sludge blanket reactor type of system. This is similar to that one. So what happens, the wastewater comes down, and from here it goes up and then go to the next tank, and then from the top it comes down and then goes again. So it is going in a series of upflow direction where the water is kept in a suspended way. So the suspension, this is called the suspension media, where the floating microorganisms which are in anaerobic condition are treating the wastewater. Treating wastewater is nothing but they are eating the small organics which are found in the feces. So this is this type is called, like we call that as anaerobic baffle reactor. So this is a closed system, so we call it as anaerobic, and we make the water go in a baffle way, so we call it as anaerobic baffle reactor. In the same thing, we also have some type of systems which are called anaerobic filter. The same series of tank wherein there will be fixed media will be kept. The media nothing but there are aggregates, so they will be kept. So in this thing, the suspended microorganisms will treat, wherein here the microorganisms will make a fixed growth there on the top of the or the surface of the aggregates, and they treat again the same anaerobic reactions. So this is the major secondary treatment where 80 to 90% of the solids are removed from the wastewater. Then goes the tertiary treatment, which is called planted gravel filter, which is again another natural treatment system where a shallow tank is about 60 centimeter depth of filter materials are packed in that. Here there are no solids or nothing, only aggregates of different sizes are kept. And you can see this is the planted gravel filter where you don't see the water at all. So in the previous modules also, these are all closed systems. So when the water goes, you don't see the wastewater. Here it is again a closed system. You don't see the wastewater. Even in this system, the 60 centimeter filter meter pack is only 50 centimeter of water will be kept. On the top, you will see only the plants. So you don't see the wastewater at all. So once the treated water from the planted gravel filter come out, then you see the clear water. So here you have not seen any energy used. You have not seen any chemicals used. And this is one such natural based treatment systems. There are similar natural based treatment systems available like phytorid, soil biotechnology, and constructed wetland treatment systems. So those are all other treatment systems which we can also try to learn, and then we can see how we can adapt that in our thing. See, the main point what I'm trying to say is that implementing wastewater treatment system is easy, but maintaining the system is becoming very difficult now. Why? Because we need to continuously have a look at the treatment systems for providing chemicals, switching on, switching off. If there is no power, then you need to have a backup system. So all those things have to be ready for maintenance of the treatment systems, which
Suparna.
Yes, I have just turned off my video. So yes, because yeah, you're back on, Mr. Andrews. We missed you for a few seconds. That's it.
Yeah. So there was a power cut. So okay. So I said about the planted gravel filter. After that, I was telling about the maintenance of the systems actually. So where we need more power and chemicals and maintenance, meaning that one skilled staff should be there. So though that cost becomes very huge, and that's why many systems failure in the long run. So, but when we go for a nature-based treatment system, the maintenance will be very much low. So, and you don't have to do it on the day-to-day basis. So that is how we promote the nature-based treatment systems. So using this nature-based treatment systems, you can treat highly polluted domestic wastewater like our household wastewater. Like for example, the settler followed by an anaerobic baffle reactor, followed by an anaerobic filter, followed by a planted gravel filter, or in a moderately polluted like a gray water. Gray water is something that the water comes from kitchen, bathroom, everything. Then we can just use a settler followed by anaerobic filter and then planted gravel filter, because this system is mainly used when the organics are more. So we need a robust system wherein in the gray water we might not have much of organics. So we directly use these kind of systems. You can even modify this kind of modules. With that, you can play around and you can customize any different type of treatment systems. Like for example, for a less concentrated, you can have a proper sedimentation, meaning water solid separation system, followed by that the planted gravel filter, or we call it as a constructed wetland. Or you can sometimes use constructed wetland directly for some of the wastewater treatment systems. So it's all depending. So you can make a lot of permutation combinations and you can modify, you can customize with this kind of modules. So the modules I told you to just learn about the process wherein the implementation can happen in a very systematic way. So we also provide this kind of ready-made treatment systems or fiber reinforced treatment systems where that can be directly fixed for a smaller colonies or some kind of apartment or one or single households. We can provide these kind of systems. So I'll try to show some of the systems. These are the systems we have implemented in the households, the household level, for one household, there is a treatment system. This is implemented in an institute called KILA. KILA is Kerala Institute for Local Administration, which is in Thrissur. So what you see is one treatment system, household level treatment system. We can also provide a large treatment systems for, this is one of the treatment system in Arvind Eye Hospitals in Pondicherry, which is actually inaugurated by late Dr. APJ Abdul Kalam in 2003. And till today, this system is functioning, and only because the maintenance and everything is very less, and the department who takes care of the system is very keen on taking the system, because this looks like a garden, not like a treatment system. Usually, treatment systems are meant in the backyard of the industry or building or everything. But here, this is the front yard, actually, front yard of the hospital. So once if you enter, you see the wastewater treatment system, then you go to the hospital. So that's how the nature-based treatment systems incentivize, the kind of nature and its promotion. So this is similar systems implemented for tsunami rehabilitation households in Tamil Nadu. We also provide the systems, the same kind of systems for water body rejuvenation. So for example, some of the drains, you might know, most of the urban lakes are polluted because they receive urban sewage, and all this, so the stormwater drain, which are meant to carry runoff, the rainwater, which always carry now sewage. So, but we provide systems like this. We divert these drains water into a DWATS or this settler and anaerobic baffle reactor and anaerobic filter based systems, followed by that we provide the treatment wetlands, then it is let into the lakes. So that's how slowly the lakes can also be rejuvenated. The same DWATS or the nature based systems can used for treatment of fecal sludge also. Fecal sludge are nothing but the sludge which are collected from the septic tanks and soak pits. People who do not have the underground drainage system, or households who do not have any other treatment system, the houses are having septic tank and soak pit. But once in 4 years or 5 years, or whenever they are filled, they have to be, desludged or excavated or cleared, and then that will be thrown somewhere else. Again, it is very indiscriminately thrown. So now cities have come to adopt fecal sludge treatment systems. So even in this, we can adopt the same nature-based treatment systems. So this is one nature-based treatment systems we adopted in Coimbatore under the Smart City project. Almost for 9 lakes, we have provided these kind of systems for rejuvenation and restoration of these lakes. This is one such lake in Periyakulam in Coimbatore. We also have provided city-level pond rejuvenation systems by understanding the quality and quantity of the wastewater which are coming in the drain, and provide the constructed wetland treatment systems as a nature-based treatment system for rejuvenation of these kind of systems. This is one bigger lake in Bangalore. Almost we have provided 1 ml of treatment using the same nature-based treatment systems, and it is functioning last 4.5 years. Earlier, you can now you can see earlier this wastewater were redirected to the other areas. Now what we have done is we have collected the 1 ml of water, treating it, and then putting back into the lake for its rejuvenation. This is one nature-based rejuvenation in the canal rejuvenation, actually in Alappuzha. So we have done this as a pilot project actually. So 220 households we have collected, and we have provided the nature-based treatment systems. So here we have provided one DWATS, the settler, ABR, AF, and planted river filters. This is the one I said, KILA, where we have provided 14 different type of household level treatment systems. So what you can see are the individual household treatment systems. Now we are doing similar project in Munnar for rejuvenation of one river. It's called Nallathanni, which is an ongoing project. Similar treatment systems we are proposing here as well. So So on the whole, what I'm trying to say, wastewater treatment systems are very important, and it's up to us how do we want to approach that. If you want to do a sustainable treatment systems, we need to think also the operation and maintenance part, where we promote the nature-based treatment systems for its sustainability. That's it. Thank you very much. I would be happy to take questions.
Thank you so much, Mr. Andrews, for walking us through the journey of your organization into, decentralized wastewater treatment, which is inspired by nature-based systems and solutions. So this was very insightful, and I was very happy to see the case studies. I'm very sure all our participants also could relate with some of the cities that you have shown, Jammu, Munnar, and other places. Thank you so much. Now we have a few minutes for our question and answer exchange. So maybe in the next 10 minutes, we will be having that with our participants. I would just like to start off the conversation with one question each to both of you, so that we can have follow-up questions and other related questions. So I would like to first ask Dr. Kirti, giving Mr. Andrews a little bit of break from talking. So Dr. Kirti, we have a few young scholars here. Could you please share your motivation and choices to select wastewater treatment and the system process engineering as the choice of your career? Like, what was the key motivation for you to go into this discipline or field of study? Thank you.
Thank you so much. And I think this is something which you build over time, like your interests. So for me, when I was in school, my major interest was mathematics, but then I also wanted to apply it to something which has real application. And then with the field of emerging computations and things, I also realized that maybe coding is something which I want to do, but not just do coding, but also look at some of the real applications. And that is what interested me. And particularly when I was doing my undergrad and masters, so one thing which I would like to share is that my father is also a faculty in India. His area was more on the wastewater treatment experimental side of things, particularly looking at advanced oxidation and adsorption. So I already had, I would say, fascination for that, seeing what was happening in the lab. So I wanted to combine and study how I could apply some of my interests of mathematics and programming to this area. And fortunately, through the other, like during my PhD program as well as postdoc, I got introduced to some of the colleagues from US EPA. So Dr. Cabezas was at US EPA before. Now he works as a research professor at Hungary. And that's how I connected to some of the other colleagues working in this area. So I think it was a combination of interests, then having somebody as a role model, and then connecting with colleagues, which helped me to develop this area. Thank you.
Yes, thank you so much. I think that, many of the young scholars here would find it very inspiring because they're still figuring out what to do in the future. So thank you for sharing your journey. Mr. Andrews, could you please share, like based on your experience, like, these decentralized wastewater treatment, a lot of science is available with us. What are the challenges in converting this science into actual practice across the places in India, and also to influence policy decisions? Because communities may also have certain specific requirements to adopt these decentralized wastewater treatment methods that you have developed. So could you please share some of the challenges and some of the experiences that you have had with the community and also the policy sphere, if any? Thank you. Mr. Andrews, we cannot hear you. You are on mute.
Sorry.
Yeah, thank you.
So this nature-based treatment systems, or DWATs, they have got a very good attention in nowadays. In policies, it has been even referred in CPHEO manual. You know CPHEO manual, right? Yeah. And in many of the policies in SBM Urban and Gramin. So that they say that decentralized treatment systems. So it could be anything. It could be any treatment system which could be implemented within near the source with less amount of energy and chemical used. It could be DWATs also. There are other technologies like phytoraid, soil biotechnology, wetland treatment systems. So all those things are now gaining a lot of attention. In my experience, I remember in 2008-9 times, we used to conduct orientation programs on decentralized treatment systems everywhere to make it popular. And there was a lot of kind of workshops and seminars and everything happened. And we were also at that time promoting trainings, train engineers to make more engineers to go and implement. So, but now the case is different. Now it has got a very good attention and people are very much aware of it. And more than, I mean, in a different level, households are asking for simpler treatment systems for their, house which is located in remote area or separate area. Resorts, they ask for these kind of systems, and in a community level they ask, and now it is coming in a citywide level actually. So even in the citywide, the cities who are already provided with underground drainage system, in order to make a 100% coverage, they are also looking how decentralized systems can be adopted to make a 100% coverage actually. So that's how now it has got a gain. And especially water body rejuvenations, solid waste management, fecal sludge management, everything has got a good attention through this Swachh Bharat mission initiatives, both in urban and Gramin. So especially in Karnataka, we have conducted a state-wise capacity building for all the 31 districts in Karnataka for liquid waste management under SBM Gramin. So it's basically how the wastewater in the rural areas and villages, how that can be treated using the small treatment systems like DWATs and other constructed treatment wetland systems. So that we have already done it, but that is also slightly picking up actually. So that's what my experience is.
Thank you so much. I
think Mr. Ajit Seshatri is here. He is our old partner, sir. Thank you so much because he knows better than me. Actually, he introduced me to the DWATs and concepts, everything. So I'm very happy to address that also.
Yes, please.
Thank you. Thank you very much.
We would also like to invite Mr. Seshadri Ajit to share his comment that he has put in the chat box and any questions for the speaker. Please, Mr. Seshadri Ajit.
Yeah, okay. No questions from my side. I would only like to give some suggestions. See, now in the last phase of our treatment, we use plants. So yes, what we are doing now is putting floating bed, so that the floating bed can be taken out, harvested, and new saplings can be put on new beds. And we are using elephant grass. Elephant grass, in Tamil you call it aanai pullu, and that is very good fodder. Very good fodder for both the cattle and goats. And if the water is used, and also the plants are used, and the sludge also is used, nothing like it, nothing like getting everything from the nature. And one more thing is, I will say that all our participants should start using less of chemical soaps, and they can change over very nicely to bioenzymes. Now, these bioenzymes, Vandana Shiva, Better India, and many other outlets are doing bioenzymes, and they are available. So that is the best. So if you use bioenzyme, the wastewater or the sewage water, other than the sewage water, do not require any treatment. Just a normal filtration will do, and that bioenzyme water can straight away go to the plants. So I request these practices to be followed, and we will get lot of water saving and water conserved. Thank you very much.
Thank you so much for sharing your point of view, and it is very well taken. I think it's quite inspiring, like we should make changes in our lives as well. And before we open the floor to the participants to ask questions, I think Dr. Kirti had a question for Mr. Andrews in the chat box. Please feel free to have a conversation, and then we'll move to everyone else. Thank you.
Okay, thank you so much. So this was very interesting, Mr. Andrews, and a few things which I wanted to understand is you mentioned about maintenance. So what makes the maintenance minimal? Because many of the high-end techniques do require a lot of maintenance. And then you also mentioned that you can treat different types of wastewater streams. So do you need specific type of plant species or materials within the DWAT system that can suit to a specific type of wastewater stream for treatment?
Mr. Andrews, please unmute. Thank you so much.
Sometimes. So if you ask, there is no maintenance actually, but there are some maintenance needed. So we used to call, it's a low maintenance system, low maintenance systems. People were always hearing no maintenance system. So that is how, it should not go. That's why we bring this maintenance as a part of it. You see, primary treatment system does not need any maintenance on a day-to-day basis, because it's only the solid liquid separation and solids are getting settled. So the design will account how much of solids can be accommodated. So maybe the design period will be like 1 year or 2 years or something like that. So if this were 1 year, after 1 year, you need to take the sludge out and then dispose that through a fecal sludge treatment system or through a sludge drying bed system. So that is the primary treatment maintenance. In secondary treatment, again, the sludge will accumulate over a period of time, like 3 or 4 years. So we need to again remove the sludge, the digested sludge, and dispose them safely. That is the next maintenance. And in a planted gravel filter, the types of plants which are having fibrous root systems, the roots which are like a thread, those type of plants are used. Like Canna indica in Tamil, like Ajit sir said, Canna indica in Tamil it is called Kalvarai, or the riverside reeds. They also have this kind of fibrous root systems. There is a plant called Colocasia that's called elephant ear plant. So that plant leaf will be a kind of size of an elephant ear, so it's called elephant ear plant. That plant also, so all these plants you can see normally in the drains. In I think you are in US, but you can see in US also. But even in India, in many of the drains, you can see these kind of plants. These kind of plants with the fibrous root systems, with the rhizome, is very good in absorbing the nutrients quickly. And the interesting part is that if you use Canna indica as a plant, it gives nice colorful flowers like yellow flowers or red color flowers, or that kind of flowers it gives. It look like an aesthetical value for the treatment system. I showed in Arvind Hospital slide, that plant is actually Canna indica. So in planted gravel filter, the filter will get clogged over a period of time, like 4 years or 5 years once. So we need to just remove the filter materials, the aggregates, wash them and put them back actually. So if you look at it in a periodical maintenance, you have to take once in 3 years a kind of cleaning the systems and put it back actually. Other than that, there could be maintenance like could be blockage, or it's all like our human errors actually. The system will not have any problem. System will not give any problem. If some cloths are thrown in the toilet, if some bottles and some bigger things are thrown, which end up in the settler or in the other treatment system, there will be a blockage. So the manholes will overflow, all those things can happen. That time you need to clear the path actually, that's all. So we don't have to initiate the treatment. We don't have to maintain the treatment, because the treatment will happen 24/7 automatically. So that's the maintenance part we have for DWAT systems.
Thank you so much. Yes, yes. So now the floor is open for questions from participants. Please feel free to unmute yourself and ask the questions. We have about 5 minutes more for this. Thank you.
I will break the ice from the participant side, and I have been listening to both of you. It's an overwhelming experience to see how a sophisticated system can be, coded and looked at, and how Andrews talks about it at a very, very, individual level, what one can do. A very interesting presentation. So first of all, thanks to both of you. I have questions for both of you. And thanks, Kirti, for decoding the P graph. I have broken my head a few times and I just gave up. So thank you. Importantly, if we want to really put up these sophisticated systems for the domestic sewage, let's say in municipal waste, we can say, how do you think we are really prepared in the country? I am aware you are working in the US, but I'm also aware you are also working in the Indian subcontinent as your case. How are we prepared, and do you think there is a role of AI which can be really brought in? And you know how our municipalities are as of today. How do you see where we are? And my question to Andrews is very simple, being an individual and a citizen. What is stopping us to really put DWATs at even the residential level or at a township level, so that the load on the municipal waste becomes comparatively easier? How far are we to really put it as a mandate in most of the, at least the gated communities, so that basically what I'm trying to say is that there is a convergence in your approach of talking about at a plot level or an individual level to what Kirti is talking about at a very, very comprehensive system design, so that also becomes easy. So where do we see convergence and how far we are? Because there is so much of impetus on water supply system in the country, and as compared to that, the wastewater system does not give that much of impetus. My common sense says that if we are putting 100 rupees in water supply, we should put at least 99 rupees in wastewater supply, which is not happening in the country. And that's why my question. So thank you, both of you, and you may choose who wants to answer first. Go ahead.
Yeah, I would like to answer your first question, which was posed to me. So in terms of how this can be applied and how is it helpful in the Indian community. So what I have seen is collaborating with actual people who are working towards designing or using these wastewater treatment systems. So for example, here in New Jersey, we are collaborating with the Atlantic County Utilities Authority, and talking to them makes us realize that these people are willing to use modern techniques. The thing is, they need it to be explained in a language which is easy for them to understand, and then is it something which we can provide to them that they can implement on a day-to-day basis. So one of the things which I did not have enough time to talk about, but we are also looking at how these wastewater systems are basically collecting wastewater from different communities they serve, and then how is it taken to the treatment plant. And then of course the treatment in the plant is based on several technologies. But the collection systems, with time, the pipelines have been eroding, and due to some of the unwanted things which get disposed of, that leads into some of the pipeline breakages and those type of events, which results in affecting the community. So what we have realized that if we can collect data, even if it is a small amount of data, and over time, and then there are some well-defined metrics in regards to what is the lifetime for a certain pipeline or for a certain unit, then we already know from some of the research perspectives that what type of maintenance and monitoring activities would be needed. And in fact, we can put sensors in places. So how to do that, as you mentioned, Mansi, about AI, we are actually using some of these machine learning methods to figure out an asset management technique whereby in analyzing the data, And by inputting the data on a regular basis, the utility companies can monitor which things need to be maintained rather than waiting for something to happen and then doing a reactionary approach. Rather than being more proactive would be better. And then combining with a better wastewater treatment design would definitely add benefits to it. Another thing which we are doing, in fact, I was introduced to the community via Dr. Girija Bharat from New Gamma, and we are working with them on some of the other projects where we want to expand this. So we have applied for grants in US as well as India to see if we can expand these efforts. And I think the key is that we actually collaborate and partner with real utility companies which are looking at wastewater treatment systems. And that's where these technologies get more attention. And then it also gets investment from agencies which want these to be implemented.
Yeah, just to add Kirti's thing, I'll just put it in a 3 different perspective. One is that Kirti's work, Dr. Kirti's work is marvelous, extraordinary in terms of selecting the treatment process for specific wastewater treatment system and your objective. So if your objectives removal of solids, removal of organics, nutrients, and something like that, then her model exceptionally, like, she can do that proper thing to select quickly. So that kind of thing I see it actually. So wastewater treatment can have different objectives. It could be, like it's multiple, it's variety of objectives is there actually. So in that perspective, I see that. In my perspective, I similarly showed the same thing. Like in some of my slides, you see, you can either choose the primary, secondary treatment modules for a highly concentrated water or a lesser concentrated water. You can customize some of the modules. So my point comes with this actually. So though both can be used in a different perspective, depending on what is your objective of treating the wastewater and why are you doing it and for what you are doing it. For example, the wastewater treatment system, nature-based treatment system can treat up to certain level where it can be just disposed in the natural environment where you cannot go and touch it or something. Wherein in come to Dr. Kirti's model, you can use the water for reuse kind like flushing or any other purpose like car washing and to the degree of treatment. So that kind of perspective I see actually. So, but the other point, what you mentioned also that if you look at this household and community level and the kind of reducing the burden for the sewer lines, I totally agree with you. This kind of decentralized models will really help the cities to reduce the burden of the sewer lines. One such example is in Tiruchirappalli. Tiruchirappalli has an underground drainage system, Tiruchirappalli in Tamil Nadu, where there are a lot of public toilets available. So the design of Tiruchirappalli, the pipelines are actually 1 feet dia. They put it in some 30 years before. And the public toilets have come newly. And you can see public toilets bring a lot of solids and wastewater, right? They cannot put into this kind of sewer line systems. That will be a big burden. Where the treatment systems like DWATs can help to reduce the solids from the public toilet and provide only the treated water into the sewer systems, which is good for the city perspective. So, I mean, there are a lot of things we can discuss like this. Thank you.
Thank you so much. Are there any other participants who would like to have, ask questions to our speakers before we close? Yeah, okay. Thank you. And before we close, we would like to thank our speakers for joining us. And we would also like to thank Dr. Girija and Mr. Nathaniel from New Gamma Private Limited for connecting us to our speakers. That is how we got in touch with both of you. So we are happy to share. We are growing as a network. and we would be also connecting you to our other speakers. And we were very excited to have you in this panel, and we benefited immensely from your experiences and your research. So before I close, I would just like to invite Ms. Dr. Mansi to introduce the next Wednesday's panel. Thank you.
Thank you, Suparna. Thanks for the wonderfully coordinating the session. And Kirti and Andrews, I have new friends to bother about my wastewater endeavors. So I will keep coming to you and bother you with more questions I have. We have our last session of the Wednesdays for Water for 1 year. So we are celebrating 1 year on 27th of April, and we are very excited to complete 1 year. And mind you, it is every Wednesday, 5 p.m. onwards. So we are really overwhelmed, and we are celebrating with a very nice session, which is a soft session, and we are going to have the crew members of the famous song of Rivers of India, a song which actually brings all the names of the rivers in India and is put together like a garland, and it's one song. And we will have Dr. Kanikswaram and E. Nandakumar, both from IIT Madras, and crew members to come and talk about the making of the song Rivers of India. So it's a soft session. We will be all interacting with the crew of the song, and the song will be also screened because it's a video. And we will really celebrate the year one. So I invite all of you to join us on 27th of April and really continue encouraging us for the Wednesdays for Water sessions. We are not going anywhere after 1 year, so we are going to continue after that as well. So the season 2 starts with more events than Wednesdays for Water. So we are really excited for it. We are working towards it. Along with Wednesdays for Water talkies, we will have PhD platforms, and we are working on few more stuff. And next week, we also announced the painting competition, which is going around for more than a month now. We have received many paintings from children and students from across the country. We are putting it in our social media, and on 27th, we are going to announce the best 10 paintings. All are beautiful, and students and children have shown their concern about environment and water. Importantly, it reflects that they are really concerned about their future as well. So we are going to show them as our clippings and also announce the winners, because we also have awards for them. So thank you very much, all of you. Please take care of yourself, and we look forward to seeing you on next Wednesday and the Wednesdays to come. Thank you very much.
Thank you.
Thank you so much.
Thank you.
Thank you.
Bye-bye.
Thank you, presenters, for joining us today and enlightening us with your wisdom. Also, thank you all the participants for joining us and making the session interactive. Besides walking and talking water, worries and wisdoms collectively, we see this as a platform to cross-connect and expand our network and explore possible collaborations. We are also making notes to publish both scientific and non-scientific work. Here is a glimpse of some of our writings. You may reach us through email, LinkedIn, Facebook, Twitter, Instagram, and also look at our website www.W4W.in. We look forward to your suggestions and comments to make the series more meaningful and engaging. And meanwhile, we hope that you appreciate today's session. We represent Tata Institute of Social Sciences, Hyderabad, Terry School of Advanced Studies, New Delhi, Environmental Design Consultants, Ahmedabad, FluxGen Sustainable Technologies, Bangalore, Counterview, and we are supported by Wiki's Water Resources Council. We truly appreciate your support and encouragement in conducting this series, and we hope that you will stay tuned with us through our social media platforms and our website, and you will write to us at our email IDs.